Okay, thanks, Frederick. Okay, so I'm going to, because we haven't had many other talks about interactive proofs, I'm going to be a bit more general in my talk and not get into too many of the technical details. Unfortunately, there's a lot of technical detail. I'm not going to be able to say very much about them, but hopefully I'll give you a good idea of what it is that I'm after and kind of some of the tools that we can use to make that happen. Okay, so first of all, let's talk about what is an interactive proof. So interactive proof is a complexity theoretic notion, and so it's a type of computation, but in contrast to normal computation where you just have a single box, a single computer that's attempting to solve the problem, in here we have, in interactive proof, we have two different parties that are participating in the calculation. Now here we have on this side the verifier, and here the prover. And these two entities have different amounts of resources, and they're going to try to collaborate together in order to solve the problem. Now, the prover over here is computationally unbounded, so we assume that they can just solve anything they like. Any computable problem, they can just solve it in an instant, and there's no bound in what they can do. Unfortunately, they're not very trustworthy, and this means that if we want to tap into this power that they have to compute anything that we like, we have to develop some means of deciding whether or not they're being truthful when they're doing the calculation. And so that's the job of the verifier. The verifier is the person who would really like to know the answer to this question. And so what they want to do is tap into the resources that this prover has. But because the prover is untrustworthy, they have to develop a method of talking with the prover and then discovering whether the prover is being honest with them. And so the way they're going to do that is they're going to have a conversation, so they're going to have some back and forth conversation, and at the end, the verifier will decide whether or not they should accept the calculation or not. So accept means, in the complexity theoretic language, that means that we accept this, means that we believe that the input is in the language. And so in order to make this go, we need to have two properties. The first one is called completeness. And that means that, so let's imagine we have some language L that we're interested in, and then we say that we have an interactive proof for L if, for every input, if the input is actually in the language, then there should exist some honest prover here that can convince the verifier that this is true. So that means that if the input is in the language, then the verifier should accept with high probability, okay? And on the other hand, if the input is not in the language, meaning that the result of the calculation is 0, say, then there should be no way that any prover, dishonest or honest, can convince the verifier of this. Okay, so that with high probability, the verifier should reject if the input is not in the language. And this second condition is called soundness. And so if you have both of these properties, then that means that the verifier can be pretty sure that they've got their right answer after talking with this prover. And if they need to, they can repeat as many times as they like in order to get whatever confidence that they want. So that's an interactive proof. Now, what we would like to do is we'd like to do this, but instead of using the kind of standard definition of interactive proof, we want to replace this prover with something else. So in the normal interactive proof, we have this imbalance between the two, between the verifier and the prover, and what we'd like to do is we're going to have a different scenario which has a different imbalance. And so we're going to have, on the verifier is going to be a classical computer, just limited to polynomial time computations, so kind of like a normal classical computer. But instead of having this computationally unbounded prover, we're going to swap out a prover which is bounded to quantum polynomial time calculation. So the idea here is that we have some kind of normal classical computer here and some kind of normal quantum computer here, and we want to decide what are the kind of languages that we can decide using this type of setup. So what kind of things, for what languages does there exist an interactive proof where we have a quantum polynomial time prover? This is what we're interested in. Now, for some very good reasons, it's actually, that problem was quite difficult to solve. And the basic problem is that there's no way that we can tell the difference between a very, very powerful classical prover and a normal quantum prover. Because you can always take, if you have a single entity and it's just communicating classically with us, we can take that quantum thing and we can replace it with an exponentially larger classical thing, and we can never tell the difference. And this means that most of the tools that we have for thinking about how quantum computations work and how we can test them don't work for us, because we can't verify that anything quantum is going on at all. And so we don't have any good tools for that. And so then we move into a different scenario where instead of having a single prover, we have multiple provers. And here we're going to have, so the multiple provers are going to be isolated from each other, so they're not allowed to communicate with each other. And once you have this scenario, then now we have some tools, because as soon as you have two non-communicating classical or quantum entities, we can do things like verify entanglement, and we can be sure that there's something classical going on between them. And now all of a sudden we have lots of tools that we can use to verify the behavior that's going on inside these provers. And so this is the model that we're going to be interested in. Yes?
Maybe I'm confused. I thought the purpose was for the prover to convince the verifier that X is an L,
yes,
and he can do it because it's quantum. What's the connection between this and proving the verifier that it has quantum behavior?
So the way that's going to, so this has come out, but basically what we want to do is we want to be sure that what's going on inside the quantum prover is actually the calculation that we want.
Not just the answer is correct.
Not just the answer is correct. Okay. So this is going to be the tool that we're going to get to the,
okay.
Yes. Yeah, so there's actually two separate questions going on, but one will imply the other. Yes. Okay. And so this is the model that we're going to be interested in, where we have a number of quantum provers who don't communicate with each other, but they're going to interact classically with a single verifier here. And so it's not really in this picture, but these guys are allowed to talk to each other ahead of time and establish some kind of entanglement with each other, and that's actually going to be necessary. But during the interactive proof, they won't be communicating with each other. But in the setup, you can see that we can usually put things like a Bell test into this type of model and verify that there's some kind of entanglement going on, verify that there's some quantum stuff happening, and then we can use that later to bootstrap a process where we verify that calculation that we want to happen is actually happening. So many people don't talk in the language of interactive proofs, but they talk about things like non-local games or Bell tests, and so just wanted to, how is this different or how are they similar? So one way of thinking about it is that an interactive proof is kind of like a non-local game, but the winning probability, or the quantum winning probability of that non-local game is somehow related to whether or not the input is in the language. So for example, if the input is in the language, then somehow this non-local game implies that there's a higher winning probability. And if the input is not in the language, then somehow this implies that there's a lower winning probability. And then the provers can convince you that input is in the language just by showing, hey, we can win this with a really high probability, right? And so that means that we can be sure that the input is in the language because we have some bound that says that couldn't happen unless the input was in the language. Another way of thinking about it is if you have a Bell test where you're interested in the maximal quantum violation, and again, the maximal quantum violation is somehow tied to the computational question that you want to ask. So that you might see a higher, if the input is in the language, then you would see a higher quantum violation than if the input is not in the language. So this is the kind of idea for how you might want to think of an interactive proof. But there's an important difference, which is that in most of these things, like Bell tests and non-local games, usually there's only one round of communication. The referee asks the questions to the players, and then the players give their answers, and then we decide if they win or not. In interactive proofs, there can be multiple rounds, so that they get some answers back, and the verifier asks another question, and they get another answer, and so on. There may be many, many rounds of communication. So this is the important difference between interactive proof and the normal model for non-local games or Bell tests. Okay, so there's a bunch of complexity theory that you might have to think about to decide, okay, is this actually an interesting question? So here's the standard Venn diagram for how these different complexity classes sit together. So we have here P, which is of course the things that we believe could be solved on a classical computer, kind of normal. We have BQP. These are the things that can be solved on a quantum computer in polynomial time. So this somehow represents also the power of the provers that we're interested in. We have NP here, which is the things that could be verified by a polynomial computer just from a certificate. And then of course we have here the outside one, which is P space, which is the languages that can be cited with a polynomial amount of space. Now there's a deep theorem that says that in fact for any language in P space, there actually exists an interactive proof. So does this already solve my problem? Yeah, no. Otherwise, this would be a very interesting talk. There's a construction that happens inside here that takes a language and turns it into an interactive proof. But the way the construction works, the prover in that interactive proof is required to solve a p-space complete problem. So it's required to solve a very, very hard problem. And we believe that quantum computers can't solve that problem, or at least we don't know whether maybe there's a special case, but we don't know anything about how that works. We don't believe that there's a way that that construction will give us a quantum computation that can be done fast. So there is some, even though in principle for any quantum computation there's already an interactive proof, it's not an interactive proof that a quantum computer can do, at least not to our knowledge. On the other hand, we have things here, NP, these are the things that can be straightforwardly verified by a classical computer without any interaction. We can just say, here's the certificate, and then they can check the certificate at will. And so for things like factoring, for example, which we have nice quantum algorithms, but are also in NP, there's no interaction required. It's just, here's the factors. You can check, right? And so for this question to be interesting, we really need to have, first of all, that p-space doesn't collapse down to p or something, which is actually not known, whether or not that happens. But we also need to know that there's things here outside of NP. So if there's problems that can be solved on a quantum computer, but not on a polynomial-sized classical computer, and are not in NP, then this question is interesting. And we believe that there are things in here. So for example, quantum simulations, for example, is probably in that space. So there are things for which this is relevant. So the main theorem that I prove is that basically we get everything that we could have asked for. That there exists, for any language in BQP, there exists an interactive proof where we have a polynomial number of quantum provers and a classical verifier that's limited to polynomial time. So basically we can take any quantum computation and turn it into an interactive proof, and there's a polynomial overhead, but it's still polynomial sized. Okay? So basically I get everything I wanted. Additionally, we get this property, which is what you were asking about, which is that the interactive proof not only certifies that the input is in the language, but it also proves that the computation was done according to the algorithm that we asked it to be done. So it's not as though it was maybe, as though perhaps a classical computer could simulate the quantum computation. We actually know that it was a quantum computation, and it was a particular quantum computation that we asked it to do. Okay?
So if you only care about the top thing,
yes,
then I would disagree and get everything we might want, but we might also want to do with a single prover.
Okay, so yes, we got everything we wanted in the model of multiple proofs. Yes. Okay. Okay. So this property here is one that's actually perhaps in the short term a bit more interesting, because you can imagine where we have maybe a medium-sized quantum computer that, say, can factor some numbers but not factors numbers which are large enough that you couldn't do it classically. Then there's no point in us verifying the computation or anything, or verifying whether or not the input is in language, because perhaps we can do that classically anyways. But we can prove that this is actually a quantum computer that's actually doing Shor's algorithm, for example, which in the medium term, where say somebody who's developed a fancy ion trap computer or something like that, and want to show this is really a quantum computer, then they could do that by using this type of interactive proof. They don't. Yes.
I can't resist. Have you tried that on D-Wave?
No.
Sorry.
Yes.
So just to clarify, when you're in a statement of the theorem, when you say quantum provers, you mean polynomial time quantum provers, and
yes,
classical verifiers, randomized polynomial time classical verifiers.
So I actually will prove something even stronger than that, which is that the provers are going to be constant size.
Okay.
So this polynomial of number of quantum size provers, which is going to be okay. So how does this work? Well, here's what the protocol looks like. And it's basically the simplest thing that you could think of. What we're going to do is we're going to find some way of calculating whether or not the input is in the language, some way of computing this thing quantumly. And we're also going to have something which attempts to decide whether or not the provers are honest or not. And we're just going to randomly choose to do one or the other. And so here's the verifier. She's going to decide, okay, this time I flip my random coin. This time I'm going to calculate. And so she asks the provers to calculate. So she does this through some interaction with the provers. They do the calculation together, and if the calculation says the input is in the language, great, she accepts. There's no if she chooses to go down this path, she completely trusts the provers. On the other hand, if she chooses to go down this path, what she's going to do is she's going to interact with the provers in such a way that she would discover if they are dishonest. In this path, there's nothing to do with the computation is involved at all. She learns nothing about whether or not the input is in the language. The only thing that she learns is whether or not the provers are dishonest. And then if they look like they're dishonest, then she can reject them there. Okay. Now, there's some extra properties that we need in order to make this scheme work. One is that the provers had better not know which is going on, because if the provers can tell that they're here, then they can choose to mess up the calculation, right? On the other hand, if they know that they're being tested, well, there's no incentive for them to be dishonest in this case, so they might as well just be honest, right? So, but it's really important that provers not know that that the calculation is proceeding. Another thing is that somehow these things have to be tied together, so that if there's a set of provers which would behave dishonestly here, then we can also test for that there. So somehow we have to be testing the same things. The things which are going on here have to be the ones that are being tested down here. So these things have to be tightly connected in a way, but so that the provers can't tell the difference, and so that their behavior on one is being tested by the other. So but we need now something to put into these boxes that works. And so for the calculation, what we're going to do is use the measurement-based model of quantum computation. And for the test, of course, we're going to use, as the title suggests, we're going to use self-testing, and we're going to use graph states. So why these two things? Well, this thing is based on some quantum resources, which is namely graph states. And we now have a test that says whether or not graph states are legitimate or not, whether they're honest or not. And here's just the thing that I said before, that it's very important that these things be constructed in such a way that the provers can't tell which one's going to happen. Okay, so what is this MBQC? So most people are familiar with the circuit model, where we have state preparation, we have gates, and we have measurements. In the measurement-based model, there's a different separation that happens in terms of the workload. So initially what you do is you prepare some large quantum state called a graph state. So this is an example of this is the graph state that I'm interested in. This is the graph, and you'll just do some entanglement across each of these vertices. Each one of these vertices is a qubit, and there's going to be an entanglement operation which is applied across each of the edges to create this large entangled state. Now, there's nothing in here that suggests anything about a particular computation other than the size. So this graph state is independent of the calculation, so long as it's big enough, right? And then what you do is you measure your qubits one by one in a sequence. Usually the sequence goes like this. I measure this one, then I go and go down, and then I come back to top here and I do down here. So I measure in some sequence that usually goes top to bottom, left to right. And what are the measurements that I can do? Well, here's a sufficient set. That's, if I use this triangular cluster state, then that's a set of measurements which gives me universal computation. And the important thing here is that the measurements are adaptive, meaning that, for example, the measurement that I choose to apply at this qubit might depend on the outcomes that I get from these other guys over here. So this is why we have to have, in the interactive proof, this number of rounds of interaction, because I need to know what that prover said before I can choose what to ask this prover. Okay, so this is called an adaptive measurement. And it turns out if you have these resources, then you can do whatever you like. You can do any quantum computation you like. And it's actually a straightforward translation from a circuit to a measurement-based quantum computation. Now, let's keep in mind the things that we need. We have to have these measurements, and we need to have this graph state. Okay, so let's just talk about the calculate part. How do we translate that measurement-based quantum computation into something that you can do with some provers which are out there? It's actually quite straightforward. Let's suppose that our honest provers ahead of time distribute between them this graph state, this triangular cluster state, and then after that, the prover is just going to basically pretend that it's a measurement box. And say prover 1 is going to hold on to vertex 1 in the graph state, and then when the verifier asks prover 1, please measure the spaces in this basis, then that's what they're going to do, and then return the output to the verifier. Okay, so they're basically just going to simulate a single vertex in this measurement-based quantum computation. And so as you can see that straightforwardly, we get the completeness that we want, right? We get that it's possible to do any quantum computation in this model with honest provers. Okay, so that's just what I said. Now what about dishonest provers? What do I actually mean by dishonest provers? Let's quantify this somehow. So we're going to say that a dishonest prover is a set of provers that will attempt to bias the calculation, right? So let's suppose that they bias the calculation by more than 1/6, let's say. We can make it smaller than 1/6 if you like, but 1/6 is good. And we don't know what they're going to do, but let's suppose that they hold on to some joint state. I don't know what it is, let's just give it a name. And they should at least pretend to look like the honest provers, so what they're going to do is they're going to accept some measurement symbol, and then what they're going to do is return something. Now, whatever it is that they do in there, they could do some very large complex computation, but in the end, what they're going to be doing is returning a classical symbol to me. That might as well, we can just model that whole process, whatever it is, as some measurement. And so when they're queried with some measurement here, let's say that m is x, so I say, please measure x, they're going to measure according to some operator, which we're going to call x prime. And then they're going to just respond with the outcome of that measurement. So you can take anything that a dishonest prover can do, and you can shove it into this model. Okay. So now we get to the test for honesty, which is actually where all of the innovation happens in some sense. This is where the work happened in this paper. And we're going to be using self-testing. So thanks to Valerio for giving a nice introduction to self-testing, so I don't have to say too much about it. But self-testing is going to allow us to characterize the different resources that the provers have. So they have some joint state and some measurements, and what we can do is we can invent a self-test which decides whether or not that joint state is the graph state that I want, and whether or not the measurements that they're performing are the measurements that I want. Okay? And what we want is that if the provers are dishonest, then they will somehow fail the self-test. So, or put it the other way around, the self-test will show that if the only honest-like provers, so say within some epsilon of honest, can simulate the honest statistics. Or put another way, if they're not dishonest, then there will be some statistic that they mess up, and then we can catch that by sampling from these statistics. Now, the good news is that for graph states, we actually have a self-test that we can do. And not only we can test the graph state, but we can also test the set of universal measurements that we need. Now, it's important that the test not be too large, so it happens that we only need to check a linear number of measurement settings, which is good, because that means that there's a relatively low overhead. And we also need this thing to be robust, so that if say the dishonest provers, or say if the provers have a little bit of noise, then that's okay. It gives us a reasonable bound on how far away they are from honest. Okay, so usually when we're talking about graph states, we talk about, because these are stabilizer states, we speak in terms of the stabilizer group. And it turns out that the stabilizer group is going to provide all the measurements that we need in order to verify the graph state. We don't have to check all of them, but there's going to be some set of correlations that we can derive from the stabilizer group for the graph state that will tell us, or that will tell us whether whether, for example, the x and z operators. So the x and z are part of the measurements, but they're all so. If we check the some various stabilizers in stabilizer group and measure them, then we can be sure that x and z on each qubit, on each vertex in the graph, actually anticommute. And then we can use the swap isometry, which Valerio had mentioned in his talk, which allows us to take whatever it is happening in those boxes and translate that into something that looks like honest behavior, and then we can quantify that with some value. There's a couple of extra measurements that are required in order to make sure that we get this universal set of measurements, which requires that we need these extra non-poly operators. And so this is where this slide summarizes like 25 pages of calculations, so apologies for the lack of detail, but if you're interested in some of the details, you can ask me later. So let's go back to what is this protocol again, and fill in some blanks here. Alice, or the verifier here, with some probability, she'll decide it's time to do some calculation, and so what she's going to do is she's going to query the provers one at a time according to the adaptive measurement that's required in order to do this measurement based upon a computation. And at the end, she calculates from the outcomes that she gets from from the provers, she can calculate whether to accept or reject. On the other hand, if the verifier decides, oh, it's time to test, they'll come over here, and in the self-test, there's a big list of measurements that you need. There's going to be some things from the stabilizers, there's going to be some other measurements for these universal ones. She's going to pick one of them at random. And she knows, for example, if it's a stabilizer, the honest provers will always give a correlation of 1, right? If it's an operator from the stabilizer. And so if we ask the provers, please measure the stabilizer, and they give you -1 as the outcome, then that's a signature of dishonest behavior, and we reject. And so all the different measurements have this property that there's one that honest provers would give more often than the dishonest provers. And so we always accept whenever it looks like the honest behavior and reject if it's the dishonest behavior. And so we only got one shot at this. We only test one of them. We choose one of them at random. And so if somewhere the players are dishonest, then somewhere there will be one of these tests that they will fail more often than they will accept on. And that will be where we get where we detect the dishonest behavior. Now, if you do this once, you haven't learned very much, right? In particular because in here there's a lot of measurements, and you might not catch. Maybe they're honest on most of them, but there's a couple that a small number where they're dishonest. We'd have to sample from this a lot in order to catch those. And so what we have to do then is take this whole thing and repeat it a number of times. And if you repeat it enough times, then eventually you hit this a bunch of times, and eventually you hit all of the different different measurements that you would need in the self-test. So there's a bit of an overhead involved in the number of repetitions. But what you get in the end is, after you've done all these repetitions, you can say that if the input is in the language, then with probability, say, bigger than 2/3, we'll accept. And if the players are dishonest, or if the input is not in the language, then with probability less than, say, 1/3, we'll reject. So we get the properties of completeness and soundness that we wanted for the card. Now, a couple of different things about how to interpret this. Well, one thing you can do is you can do your repetitions in parallel if you like, and then in that case, each prover does only a single 1-qubit measurement if they're honest. So you have a polynomial number of provers, but each of them only has 4 different measurements, and all it does is it measures one of those 4 measurements. So it's very, very simple provers. Another way you can think about this is imagine that's just sequentially. In that case, the configuration of the provers is exactly what you would do if you were just going to do the measurement-based quantum computation by itself. So imagine that somebody invents a nice ion trap computer that implements this triangular graph state, and they can say, look, we can do all these computations on it. Well, what you can do is you can take that quantum computer and you can turn that into an interactive proof only by changing the classical control. You don't have to do anything to the quantum part. The calculation, in fact, when you do this, if you decide to calculate, it's exactly the same that you would do if you trusted them. Okay, so there's no change in the calculation that's required. It's just an additional set of things that go on top, just as part of the classical control that turns it into an interactive proof. Okay, so what is this polynomial? Well, there's the polynomial. This is the overhead. So this is, if you like, the number of repetitions that are required. It looks pretty bad. So 10 to the 50, n to the 22. I had to check. And yes, for reasonable numbers of n like 2, this is actually smaller than the size of the universe. So in that sense, at least it's practical. It's worth noting that the RUV paper is, or the Ricard-Adel paper, the exponent on n is 8,192. So I was very brave and decided I was going to actually calculate my polynomial and then just let it be out in the world. So at least I have an improvement on that. It's good. There are, I guess, in terms of the landscape, what's happening in this area, there's at least 3 different proposals compared to mine. So there's the Ricard paper, and then Joe Fitzsimmons has just recently posted something in the archive. His has n, the exponent on n is 4, so this is good. And then there's also a proposal from Elham Kashafi's group, and I believe the overhead there is, or the exponent there is 2048. So even though this looks, just if you take it in isolation, it looks pretty bad. It's actually compared to other things, pretty good. So, but with that, thank you.
When you said, in one of the very last slides, that, yeah, this one, only a single 1 qubit measurement per prover.
Yes.
You mean per prover per repetition?
Well, if you can do this in parallel, in this case, there actually is only one per prover. You can do the repetitions in parallel if you like.
Oh. Oh, so you have a large number of these graph states.
Yes.
And okay.
Yeah, you just have a number of copies.
Yeah, sure.
So you have this many copies,
Yeah.
which is quite large.
So you mentioned you can handle error scaling as the inverse polynomial. Is it conceivable that a constant error could also be tolerated?
Well, so you mean so
Meaning when
that doesn't scale in the size of the graph.
Right. So when as a prover, when I measure, I have 0.001
Yeah.
chance of getting a wrong answer.
So I think the answer to that is probably no. And the reason why is because you can imagine that you have n provers, one for each vertex, and you can imagine that each one of them, their measurements are off by a little bit, and somehow this might compensate for a large difference in the underlying graph state. So I think that probably something that scales in n is necessary, but I'm not sure.
So I think you just mentioned there's like third proposal, even third proposal for measurement based on computation or for the time?
For interactive proofs, yes. So the Reichardt et al. Paper, for example, doesn't use measurement-based quantum computation. It uses a different model of computation to get interactive proofs.
Okay, so I mean, what's the difference between your paper and
Okay, so between my paper and the Reichardt paper?
yeah. I mean,
Okay, so mine uses measurement-based quantum computation in graph states. They use multiple copies of maximally entangled qubits, so like EPR pairs, and then they have a different computation scheme, which is based on teleportation and some magic states and stuff. Then there's the two other proposals, Joe's proposal and Elham's proposal. They use measurement-based quantum computation, but they have an additional layer of fault tolerance, so that they get this authenticated quantum computation. And then they use, well, I'm not sure about Elham's, but Joe's group uses EPR pairs. Is that right? Yeah.
We don't use fault tolerance, so Elham does.
Oh, you don't? But you,
Yeah.
okay.
We only have fundamental gap between standards and
Okay. There you go.
but in terms of the number of provers,
So in the Reichardt paper, they have 2 provers, and Joe, you have 2.
no, ours is like yours.
Okay, yeah. So Joe's is a polynomial number, and Elham's I have triplet.
Okay, so I think we should end there. So let's thank Matt again and for the speaker.